We're really excited. I'm really excited today to have Paul Gradl and Max Haot here on the panel. They're doing amazing things with additive manufacturing in space. And so what we're going to do to short intro for both Paul and Max, then they'll each take a few minutes to talk about some of their kind of recent applications, and then we'll be as quick as we can, we'll get into discussion mode, Q&A. So first, let me do a short intro for both Paul and Max. So Dr. Paul Gradl is a principal engineer and subject matter expert on additive manufacturing for liquid rocket engines at the NASA Marshall Space Flight Center in Huntsville, Alabama, and works both development and flight programs. He is an associate fellow of AIAA, has authored and co-authored over 75 journal articles and conference papers, publishing a book on metal additive manufacturing for propulsion applications that came out in late spring 2022, and was named one of the most influential personalities of additive manufacturing in 2020. And he is going to be recognized tomorrow night as the Engineer of the Year by AIAA for 2022. So that's very exciting. Congratulations, Paul. Max Haot, he's founder and CEO of Launcher, the high-performance rocket company founded in 2017 and based in Los Angeles. Previously, Max was founder and CEO of Mevo, a hardware company producing live streaming video cameras acquired by Logitech in 2021. Prior to this, Max was founding CEO of Livestream, which was acquired by IAC in 2017 and became part of Vimeo. Earlier in his career, Max led technology for IMG, leading a software platform to acquisition by Verizon in 2005. Max has more than 25 years of experience as an entrepreneur, leading successful exits for all three of his previous ventures. He has a lifelong passion for space exploration and its potential to advance humanity. So it's really special to have both Paul and Max on this panel, and I'm really going to be excited to hear what they have to say. So I think what I'd like to do is we'll start with Paul. And Paul, let me share your chart, and then you can talk about it here.
Good morning, everyone, and Scott, thanks for having us, and Paul, good to see you. So.
Yeah, you too, Max. Looking forward to discussion. It's always fun to geek out on additive for propulsion applications.
Okay, Paul, let me know. You should be sharing now.
Yeah, so it's coming up here. So the group that I'm working, we are responsible for component development for both development and flight programs for liquid rocket engines. So the components that we're engaged in, combustion devices and turbo machinery, so injectors, nozzles, chambers, rotating machinery. Most of the components that are critical and of rocket engine operations. We've been involved in additive manufacturing for about 20 years at Marshall. And it's really been the last 10 years we've been heavily focused on trying to implement additive manufacturing into these applications and trying to mature it for both our own applications and also to infuse a lot of the technology to the commercial space industry and government organizations on this. So the chart that I have up here is just some examples of some of the different components that we've developed the last few years. In the upper left-hand part of the slide here, you can see examples of combustion chambers. And NASA has been really focused on developing and maturing some unique alloys, particularly some of the GR Cop alloys, which are a copper, chrome, niobium material that have really been enabled by additive manufacturing and allow us to operate very high performance chambers, very high wall temperatures, heat fluxes on those chambers. And also we've developed applications using bimetallic additive manufacturing techniques where you can see some of these chambers with both the copper alloy and some of the different super alloys. On the right-hand side, you can see some examples of rotating machinery, inducers, impellers. There's some injectors and some other complex components enabled by laser powder bed fusion. So I think, powder bed fusion has been one of the go-to technologies for a lot of liquid rocket engine applications that we're working, but it doesn't fit all of our needs. So in the center part of the chart here, you can see some examples of directed energy deposition, some very large parts, such as nozzles. And the one example there, you can see it's a nozzle. It's almost 2 meters in diameter and almost 3 meters in height, which is one of the areas that we're really trying to advance additive. So I know we're going to talk a lot of details about the process and maturation of it. The bottom part of the slide here, you can see some examples of hot fire testing, because one thing that's important for us is, understanding the processing and materials and post-processing, but also trying to mature the different techniques and increase the technology readiness level, again, so we can infuse into our applications in commercial spaceflight. So really looking forward to chatting with Scott and Max on this. And I know Max has some really awesome stuff to show as well. So I'll hand it over to Max.
Great, thank you, Paul. And
yeah, thanks, Paul. Let me bring up your chart, Max.
Great, thanks. So I'll start with the quick introduction while we do that. So I'm Max Haot. I'm the founder and CEO at Launcher. So we're a launch company, so that takes our customers' small satellite and bring them to orbit. We have a key differentiator is that we're agnostic to the way we do it. So we are developing 2 products. The first product is called Orbiter. It's a Space Tug, and we'll see some of the parts that you see on this slide to describe it. And it flies to orbit on SpaceX Falcon 9 this October. So it's our first product with customer. And what it does, it has a small propulsion engine, ethane and nitrous oxide, pressure fed, gas stored as liquid. And so that with about 300 pounds of thrust, it can change the altitude and to some extent the inclination of this satellite and provide customized orbit after they use the rideshare bus of SpaceX. And then we're also developing our own launch vehicle from the ground, which is scheduled for first flight in 2024. And one of our key differentiator is that our small launch vehicle can take 150 kilogram to low Earth orbit, but there's a single turbopump-fed closed-cycle engine on the first stage. So that means it's scalable. And our goal is to build the highest performance and inherently lowest cost because of 3D printing. 3D printing doesn't really care if it's a high performance engine or a low performance engine. That's the design part. And the materials are usually the same. But our goal is the highest performance engine in the world for small launch vehicle. And I'll talk about some of the innovations and some of the traditional technology we are bringing and obviously applying to additive manufacturing. So these are 2 products, and I'll go through all of these images and also give you some parts I have behind me. So top left, it's a combustion chamber with an injector, pressure fed for this testing, but this will be coupled with our turbo pump, which I will talk about. It's 10-ton force of thrust, 22,000 pounds of thrust. It is the right nozzle and expansion ratio to have a flight for a first stage. And it's uniquely cooled using liquid oxygen for the throat and the cylinder, the part that has the most heat flux. And we use actually the fuel, which is what's traditionally used for the nozzle extension, the piece after the throat. We were lucky this development actually came through some of the inspiration of what Paul had been doing before we met him with I believe, Aerojet Rocketdyne, where they applied a copper alloy to powder bed fusion. And in the small launch industry or the commercial industry that we're in, no one had yet done that. Everybody was using 3D printing for region-cooled combustion chamber in nickel alloy. So inspired by this, and with a partnership with EOS and one of their subsidiary called AMCM, we basically developed these combustion chamber for subscale in copper alloy, copper chromium zirconium. We don't use the more advanced alloy from NASA GR-COP. And then we scaled it from 1,000 pounds, where we had a successful, we've successfully reached highest performance. You can see the second picture. This is a copper printed, LOX cooled 1,000-pound subscale demonstrator, and we reached 98% efficiency to the point that for a kerosene engine, there's a blue plume, which maybe Paul can tell us if he's seen it somewhere else, but we still haven't found anyone able to do this with kerosene. And then since then we scaled. That's a picture you can see there on the left, with the support of a Space Force grant to help us develop it. And then we also have a relationship at NASA Stennis Space Center for testing. So this is our dedicated test stand. Last week, you can check our website, the updates. We successfully did a 10-second run at the nominal pressure and combustion temperature and of this chamber. The picture on the right, top row, is our headquarters. We have a 24,000 square foot facility. In our first 4 years of our existence, we were very small and did everything with third-party providers. We now have 60 employees, which is small by aerospace standard, but big from how small we were. And we have obviously CNC capability, welding capability, integration capability, and 3D printing capability. So right now we have, you can see the picture right underneath. We have 2 Velo 3D machine. It's one of our key partner for Inconel on one machine and titanium on the other one. We have on the left of that an EOS M300, and then later this year we have 2 large format 3D printers with a meter tall build volume in copper that is coming in. In addition, for our Space Tug, you can see the image in the middle on the left. We are building Inconel chamber, 3D printed on Velo. And if you look at the bottom right, you see a propulsion tank. Orbiter has 8 of these titanium 3D printed tank. And so one of the key reasons we use EOS and EMCM is for the large format printer and the copper. And another reason we use Velo, another vendor, is because of the ability to do low overhang that we've not succeeded with others. So an example, this is if you see the video, this is a 3D printed pressure vessel for ethane and nitrous oxide, which was printed on Velo 3D with very low overhang, as you can see right there. So this is a test a qualification article, and Orbiter has 8 of them. You'll see also we can print. This is an example chamber with a uncooled extension and a cooled in nickel alloy, and this is for Orbiter, the Space Tug. So this is in-space propulsion, printed on Velo 3D. We'll not talk about the turbo pump. This is, for example, aluminum turbo machinery for stage combustion pump. This also has an Inconel part, and all the rotating components are also 3D printed, which I can't show due to ITAR, but we print the impeller that we tested at 30,000 RPM and about a megawatt of power and 320 bar of output pressure with Velo 3D. So if you look at the slides, I think I'm nearly done. Yeah, you can see the turbo pump in the bottom at the middle that we also test at NASA Stennis. On the right, you can see a test fire of the E2 engine, the 22,000 pound thrust engine of that picture. And the two are coming together at the end of this year in a long duration test at NASA Stennis. So, two quick words. Without additive manufacturing, startup like us and others in the industry would not exist. The ability for us to start small and grow, not have any tooling, and be able to do regen-cooled chambers is really unprecedented, and obviously pioneered originally with SpaceX, and then Rocket Lab is the first one to take it to orbit on a launch vehicle, and the whole industry is using it. Launcher believes that we're at the forefront on the commercial side with our LOX cooling, large format, use of copper, in our high performance, high pressure pump built using Velo 3D and now our Space Tug. And then a lot of the innovation that, we have a relationship with Paul. Part of Paul's, goal is to bring technology to the industry, and we're very thankful to that. It started with the copper inspiration, and we also keep in very close contact for all of their testing. We're very interested in bimetal chamber. That's next for us, and also the nozzle extension, the large format that Paul showed with directed energy deposition processes. And we met 3 years ago, and thanks for the invite, Paul, to be here.
Max, that was great. And Paul, what a what an amazing company you've now got, Max. And so I'd like to kind of start off with some questions. I just want to, let's see. So, you know, kind of, which is kind of general, you probably touched on it, but for what you're now doing with the additive manufacturing, how would you articulate the true benefits of additive versus alternative approaches? And Max, you started to talk to that, but if you might say a few more words.
Yeah, each component is obviously different manufacturing challenge. You know, the 3D printing, is a compromise, or additive manufacturing, if we want to call it that way. One of the key compromise, firstly, is the size. You are limited in the size of the parts we can produce. For combustion chamber with regenerative cooling, which means you have very small cooling channel inside the wall. You have challenges with inspection and cleaning. And then lastly, it's a lot harder, or at least you need to develop new technology, as Paul alluded to, if you want a bimetal product. And the state of the art for liquid rocket engine combustion chamber is not single metal. It's copper liner, which with cooling channel, with a brazed Inconel jacket or other type of steel alloy. Now, all you need to know about the impact of 3D printing is that there are very few companies in the world that have access to the ability to make these combustion chamber bimetallic brazed reliably. SpaceX is one of them, obviously Rocketdyne, there's Russia, China, there's companies in Europe, but it's very, very, very few that have developed the process with a reasonable yield, and obviously have all the tooling and the vacuum oven and so on for this brazing. It's also very laborious. And Paul will talk about that, even the companies that have access to this technology, just an alternative one is also using tubes, a braze tube, which is very high performance and great, but even more expensive. But the companies that have access, have this tooling, can do it, are all investing to switch to 3D printing as quickly as they can. And so that just tells you everything you need to know. For us, that technology was not available. So 3D printing is the ability to even exist, right? The shortcut to be able to do it, with some of the compromise that we are challenging, obviously with large format printers and experiment with cold sprayed bimetal. But for even the traditional companies, it's really the direction they would like to go, and I'm sure NASA and Paul has more to say on that.
Yeah, I think probably one term to summarize what Max was saying on that is complexity. We can get a lot of complexity in additively manufactured parts that is challenging with some traditional techniques. We can make designs that we could never make before with all these internal features. Another advantage, I think, additive is some of the novel alloys. There's new materials that we can process that we couldn't make traditionally. I know that NASA just put out a press release about a week or so ago of the GRX 810 alloy. And this is oxide dispersion strengthened material that came about because of additive manufacturing, and we're able to increase temperatures much, much higher than we could with some of the traditional materials, and get much more performance out of that. I think the obvious one that we all talk about is just the economics of it. We're able to reduce cost significantly in time to market, or even the design iterations of it. And one example that I always give with that is 20 years ago when I started at NASA, we were running hot fire tests maybe 4 to 5 times per year for different programs, 4 to 5 programs per year. Well, now we're running probably 15 to 20 programs per year because we're so hardware rich. Before, it took so long to make the hardware and you were waiting for the hardware to get to the test stand. Now we have so much hardware, we have backup hardware, we can move so quickly on the iterations of that hardware. So you can, find an issue that you need to resolve on the test stand and be printing in a couple weeks and, have that hardware back on the stand with those design iterations. And I think that's a huge advantage, for us from an engineering perspective. It's kind of like the engineer's dream, being able to go through all these design iterations. And then another big one that Max alluded to is just part consolidation. I'm able to take an injector that had 200 pieces and able to make that in 2 pieces now. So I eliminate all of those interim process steps and the brazing operations and the inspections that go with that. And some of that is overlooked a lot, that in aerospace, right, we are extremely critical of the quality, whether it be traditional manufacturing or additive manufacturing. And any process step that I do, I'm going to make sure that I have full traceability of that. So if I'm performing a weld, I'm going to inspect that weld. So if I have 200 welds, I'm inspecting every weld on that. With additive, I can eliminate a lot of those welds that I don't have to inspect. But I think also, a point that I'd like to make is, don't use additive unless you have to. There's still a lot of great traditional manufacturing techniques that are going to work great, and they're probably going to trade really well. They may trade better than additive. So just because we have additive does not mean that we have to use it for everything. And it has to be traded with all those traditional techniques, and looking at the entire life cycle of it, not just the printing process, but the post-processing as well. So it's easy to get caught up in the hype of some of additive, and certainly there are a lot of applications it definitely makes sense, particularly complex parts, unique alloys, and some of the economics of it. But we need to apply it methodically and intentionally.
Yep, fully agree with that.
So I'm gonna that's gives us a great perspective. And one of the things I was really excited to hear about, as Max was describing his stuff, is the opportunity for, work you're doing, Paul, to influence the stuff he's doing. It's rare to find that those kinds of pipelines where you can kind of get both the technology and the lessons learned across into practice so quick. So do you want to comment on that? Has this been unique for you to have that level of opportunity for transition?
Yeah, I think that sometimes it's viewed that government and commercial space is competing, and I completely disagree with that. I think we are complementing each other really well. We work with all the commercial space companies and really a lot of the companies across industry. And from the government side, our role is to advance and mature the technologies, allow it to be accessible. And the advantage for us in the long term on that one is if we have more launch providers, that are well established on this, then we can go do more missions, and not just us, but across the commercial realm as well. So there's a ton of opportunities there. And again, we are working through a lot of those. So some of the opportunities that I think come to mind are, new alloys, like I mentioned, the GR COP, taken on some of that lower TRL development that industry may not want to take on some of that risk and some of that investment. So we can do that, and we can mature those alloys. We can develop the properties. The GRX 810 alloy is another one that I mentioned. The very high temperature material for injectors and turbine applications. And we can move fairly quickly on some of that too. So NASA can take that risk. We can try to evolve the supply chain, the feedstock side of it, work with commercial vendors to do the printing of that, doing hot fire testing to mature the technology readiness level, and then publishing those properties and getting out there and allow others to build upon that too. So that definitely, excites me on the opportunities available there. Now we're also trying to look at all the processes across the board. So we're not specific on one additive process. We're looking at powder bed fusion, we're looking at DED, we're looking at cold spray, additive friction stir, deposition, ultrasonic AM. So we want to be able to have this suite of different technologies available and have a good understanding of those, as well, because I think you tend to use what's in your toolbox, right? just because you don't have the data. So I think if we can provide that data, and that's a really good role for the government to play on this, is taking some of that early risk and then infusing that to industry. And, you know, we like to get feedback as well. Max and I will talk, and he'll say, hey, here's my pain point on things. Here's some of the needs. We say, okay, well, we're hearing, you know, that similar message over and over. Let's take that and let's go mature that. Let the government take on some of that risk. And, you know, in the end, it's going to help all of us.
Yeah, I mean, to give a practical sense of how it works, we've talked about the copper, but Paul's group obviously, you know, not only does testing and development, but also write a lot of detailed technical paper that are accessible through processes. And so, you know, the two other things we're looking at together is, for example, bimetallic. So as a startup, we can't just go and try the 10, 20 methods that are there to apply Lincoln jacket, you know, cold spray, HVOF, many other options. It's impossible for us to test them all. We don't have the time or the resource. And, you know, Paul's group has been in the background doing that. And when we get there, we have access to at least some of the information on what succeeded and what didn't. And it can allow us to narrow what we'll be focusing on. The same is applying, you know, right now we focus very much on powder bed fusion, and we've managed to push the industry with our partner EOS AMCM over the last 3 years to create a printer called the AMCM M4K that's 45 centimeter by 45 by 1 meter. And that resolved the challenge for us to build basically the first stage combustion chamber in one piece. It's something our chief designer wanted to do. Others in the industry have either built smaller engine or have built a combustion chamber in 2 or 3 parts, but it reduced performance, add complexity and weight. But beyond that, we have a second stage nozzle extension to build for our next rocket. And that's much bigger format that probably is reasonable for powder bed fusion. And we're already aware and track the work that Paul is doing with direct energy deposition. We see the updates, the materials, the cooling channels, the size, the partner, and it's really great to know when we get there, we're going to be able to have that conversation, review the paper, talk to the vendor, and sort of get a shortcut. And also, we know that this technology is there and is being developed, and so we don't have to worry about it now. We just have to, you know, hope that Paul continues and does even more. And by the time we need it, we'll be in touch with it.
That's a great story of a partnership. I want to go to a question from the audience now, and one that's been getting a lot of votes is a question for Paul, which are, what are your thoughts on additive manufacturing used for satellite? That's to work on that.
Yes, I think we're looking at all opportunities to infuse additive manufacturing where it makes sense. And I know there's a panel later this afternoon, which will be a really great one to sit in on, you know, about using additive manufacturing in space and interplanetary on this. So we're definitely looking at that. You know, from satellite perspective, I think additive and not just satellites, but I'll say even like aircraft, a huge growth area for additive is MRO, the maintenance, repair, and obsolescence. You know, parts that you can't make anymore because they were from a specialty supplier that may not exist, or you know, we don't have the drawings to make those parts, so we can go scan them and reverse engineer them and additively manufacture those. You know, so there's obviously logistics involved with using additive manufacturing on orbit. And NASA has been exploring some of that on the International Space Station. We've done 3D printing of polymers on orbit. We are working some trades now on putting a metallic printer on orbit, and it's going to be for all those critical spares, whether it be the space station or, you know, potentially as we need replacement parts when we go back to the moon and onto the Mars on that. So there's a lot of opportunities to use additive, both metallic and polymers, again, for those critical spare items, because you can't take everything with you, certainly. So you have to be able to create that on orbit and in space.
Great. What a great vision for future support. Another question from the audience. How does additive manufacturing material variety correspond to thrust applications? Are there enough alloy options? For both.
Yeah, we certainly don't see that as a. Oh, sorry, Paul. We certainly don't see that as an issue for us. You know, for example, we know that people have successfully 3D printed uncooled nozzle extension in niobium. We try and do everything we can not to use it because it's very expensive. But we certainly see at least a wide range enough of alloys to design to. That's on our side.
Yeah, I think, you know, if you look at additive up until a few years ago, there was probably only a dozen alloys that were mature, and you still find a lot of those alloys, the Inconel 718, 625, there's some of the stainless family, Ti 64, some of the Haynes materials, Haynes 282. So there are a variety of alloys available in the different families, you know, including some of the refractories. Over the last couple of years, we've seen significant growth of that too, that you're seeing a lot of these alloys matured. There's more research on them from academia, more infusion into applications. And I would say still for the most part, though, there's still a limited number of very mature alloys where we have large databases and, you know, extensive properties on these. And you have to look at them in a case-by-case basis, that there's certain companies that are developing some of their own properties and maturing those databases. We're trying to take on some of that work as well, because we see that as a big gap, you know, having large statistical databases, you know, of 50 or 100 alloys. Because if you look at traditional materials, there's thousands to choose from. So we're limited in this sense compared to traditional materials, but we're also seeing a lot of new materials advance, which is fantastic. And I think we're going to see performance improvements from those new materials that, you know, didn't exist before.
Great, thank you both. We've got a couple other questions that are getting a lot of attention that I'm going to. So first one is, how would you address the post-processing challenge of additive manufacturing components, especially those with complex internal architecture, i.e. powder removal, inspection of high density components?
I'll start on this one and I'll let Max jump in, but this is probably one of my favorite questions. We tend to focus very heavily on the process itself, right? I build a part, it looks like the geometry that I'm expecting, cool, I'm off and running. But that, I think, is the furthest from the truth. You are not going to be successful in additive unless you look at the entire process. So you have to design for additive. You have to understand your feedstock. You have to understand your parameters that go into the process to making sure that I'm producing a consistent material. And then the post-processing really is key to a lot of this. So as it's mentioned there, the powder removal, you know, removal from the build plate. How am I going to machine these parts? You know, there's nothing more painful than designing a complex part and handing it off to your machinist and saying, hey, I need you to machine these areas. And he's saying, well, I don't know how to hold this part. And I mention that because we have made those mistakes. You know, the other challenge is powder removal. We have lots of trophies on our desk of parts that we could not successfully remove powder from that. So there has to be a lot of attention in the post-processing. And then inspection is definitely a challenge. So we often say that, you know, inspectability is the inverse of complexity. So I can make a really complex part, but how am I going to inspect to make sure that I have the right geometry in there, that I don't have trapped powder in there, you know, that I don't have any defects or anything in there. So there's still a lot of development that I think is that we're going to see in the coming years, particularly in the post-processing areas.
Yeah, you know, on our side, our first full-scale engine failure was due to you know, couple. You know, there's about 100 cooling channels and only a couple, so 2% were clogged, and that was enough to be a failure. You know, thankfully, the biggest issue we have with inspection and so on is the cost. So thankfully, for example, for our next test, we invested in CT scanning, but this is about 50% of the part costs. So that doesn't make a lot of sense. And then we added inspection orifice and developed a simpler method. And then later on, we partnered with a company called Solicon, which is a depowdering machine. So there's a lot of people working on the same problem, like, for example, trap powder. And there are solutions of varying effectiveness and cost, but they are there, right? We did find a solution, and now we reliably, we don't fall for this problem. The other piece, obviously, machining. That's a really interesting point. There's a few parts at Launcher that we successfully just print and then cut off the plate and use. That's the goal. Structural parts and so on, because at the end, the goal is cost reduction. So when engineers are able to design 3D printed parts that do not need any support, can just be put on a build plate, and then can just be cut off the build plate and used, that's great. In reality, 90% or more of parts need to go and get CNC machined. And so the key is how do we, as Paul said, how do we make sure that we have it can be fixtured and so on, but also how do we minimize the time on the CNC machine, which the productivity is much lower. And so at Launcher, we have 3 2D printer and about 5 CNC machine, and the bottleneck is always a CNC machine. Because the advantage of the printer, even though a build can take a week or a few days, is the density of it and the fact that it's 24/7. Somehow mean that we always backed up with the mill. And then the other side, if you take this example, this is a pressure vessel that is to fly 8 of them on a Falcon 9 rocket, with 1,000 psi of gas, propellant, ethane, and nitrous oxide. And so we get it to this stage where it's been obviously 3D printed, powder cleaned, cut off the plate, machined, chemically etched, and now we have to qualify it and obviously do acceptance testing. And at that point, we sort of are entering, the process defined by the range, to let us fly, which has been designed for traditional tank, but we expect it to perform for 3D printed or additive tank. And I'm sure NASA is also working on additional standards for inspection and so on. But often right now, we hope that even though the part is made using 3D or additive manufacturing, we can still get it approved through the traditional process, but it has to obviously perform and be reliable.
Well, that's great insights. I see we've only got a couple minutes left here. So more questions. I don't know if at some point you might be able to, in the chat, maybe address some of the questions, but I wanted to give you each a kind of an opportunity just for closing thoughts. I know myself, I've learned a lot about the current state of the art, and I'm more excited than ever in terms of the opportunity of additive manufacturing for space. But so, Paul, last thoughts from you?
I think we're still at the adolescent stage of additive, that we have a lot of development in front of us. We're going to see a lot more applications of additive, more creative designs and additive, but we have to apply it safely. We need mission success. We need to keep our astronauts safe on this. So we're going to take a methodical approach to it. We're developing a lot of the standards and certification to how to apply additive safely. Like I said, there's a lot of processes that I think we're going to see advance. The post-processing side of it, data management is going to be a challenge that we're going to see in the future, because you're creating so much data. I think Max alluded to, some of the inspections and in situ inspections. I think we're going to see advance. And then something that I hope that we see as well is more sharing of data across the community. As we work with the commercial space partners, there's a lot of data being generated, and as a community, moving forward, I think we can be sharing some of that data and building upon what each other are doing. So I'm excited about the future of additive and the future of space as we go forward to return to the moon and onto Mars, and certainly additive parts will be involved in that.
You know, from my point of view, firstly, thank you for having us today. You know, it's interesting coming from different industry into aerospace and additive. You know, there's been you know, sometimes you meet with sales team and, you know, the industry is sort of flat in terms of growth, or has been, and you have to really zoom out. You know, from my point of view, a lot of things are still not additively made or considered for additive. Obviously, not every part should be additively made because of either traditional design or lack of experience by designers and engineers. And I think as you see people graduating and people that are in high school today or in college coming into the workforce, and over the next 20 years being in this design position, you know, I think we're very much not even in the teenage year of additive, but I think in the infancy. I don't think any, you know, development factory like ours won't have, you know, a decent amount of 3D printed additive solution, and it will be the go-to for every designer. So demand, in my view, whether it's service provider or machine, and obviously capabilities, as we've discussed, that are increasing. It's only getting started, and I've only had the benefit to make 3D part or lead a team that makes and design 3D aerospace part with additive in our tool chest, and it's very clear when you come from that perspective, when you never worked without it in the process.
Great. Well, thank you all. We have actually come to the end of the panel, so thank you so much for participating. Gentlemen, if I could just ask you to turn off your cameras and your microphones,